Checking model conditions. So when we are working with regression, there are a number of assumptions that we make about the quality of the data and the relationships in the data that we're modeling with this linear model. And generally, there's four main conditions that we need to make sure are there so our model actually is valid, makes sense, and it's not just numbers floating around on the screen. So one is the residuals of the model are nearly normal. Now this is less important for larger data sets, but generally it's good to have. Number two, the variability of the residuals is constant. So there's not that much variation on the residuals across different values of the data. The residuals are independent and they're not dependent on some other kind of value or variable in the data set. And each variable is linearly related to the outcome. Remember, this is linear regression, so we expect that each of the variables, the predictor variables, are linearly associated with the outcomes, but are not linearly associated with each other. And we'll talk about this one as well. I should have written here, but it's not a killer, but it's also important to think about. Okay, so let's talk about these more deeply. So first, normal residuals. So the residuals of the model are nearly normal, we want to ask, and we can do a histogram of the actual residuals. And just to kind of remember, so what do you mean by the residuals? Well, let's remember that, so let's say we have the data. Let's look at what does the data look like. Okay, so we have the data set, right? We use the data, an actual real data set with data of input there, let's say borrowers, people with their actual interest rates and the bankruptcies they have had. And we're going to have a outcome variable, maybe that's the interest rate, and we're going to have a predictor variable that's X1, maybe it's bankruptcy, and then another one is X utilization, credit utilization, and some other income of the borrower, and so on. And another one, we can also have the predicted Y. So after we create the regression, we can simulate the predicted Y values based on what the line would be, if we just continue regressing. So let's say we have points all over here. This is our data set. And you say, well, let's say this is rate and this is like income. Well, the higher the income, the higher the interest rate, or maybe actually this would be a negative relationship, but let's assume for just the sake here. Okay, I see there is a linear relationship. So what if the income was here, all the way over here? What would the model predict the rate to be? Well, we'd predict to be right here. So that's the predictive value. That's the predictive value right here. So that would be here. Now, if it's all the way over here, we may not actually have a Y value for that, but given all the other X1 and X2, all the other predictive variables that we have, we can have a predictive value for all of them. And then the error rate, the residual, this is the residual here, is just the Y minus Y hat. Okay, so the residuals is 3, 4, 2, whatever the numbers are, the residuals is this here. So it's kind of like a variable in the model. So you can, just like any of the other variables, we can get a histogram of that, and if it looks normal, or nearly normal, that's a good thing. The variability of the residual is nearly constant across data points. So here it's kind of like a scatter plot of the fitted values and the residuals. So the idea here is that the fitted values are well, actually this is the white hat. So we want to see that the actual predicted values and the residuals, doesn't seem to be a correlation there. Okay, we want it to be like calling up all over the place. And here they put a kind of line, it doesn't really look correlated. So we want to see a good distribution around, otherwise if we see some correlation, that kind of screws up the model. The residuals also do not seem dependent or correlated on another variable. So like, for example, time of data collection. So you see here, this is a graph. So this doesn't seem correlated. And if you want to compare with many other variables, you can do it as well. once again, the residual is kind of like, after you create the model, the residual is just another variable of the model that you can plug into your data set. So you can separate. So for example, for all the people that have had bankruptcy, for all the people that have not had bankruptcy, how are the residuals? Do we see like a correlation? Here, this box plot, these two little, do these look different to you? The people that don't have bankruptcy, are their residuals much different than the people that have had bankruptcy? Slightly different. I'm not sure. I would not say this is terribly different. I don't see like a correlation between these two, meaning that one is so different than the other, then it could be correlated. But that's the idea here. You want to check for this independence of the residuals. And linear association. So this is association between predictor and outcome variable should be linear. This is a linear model. So, you know, if we see something like, and the way to do this, a good way to do this is the scatter plot like this one here. So for example, let's say, suppose you're checking something, and it could even be this, like advertising versus revenue. And suppose if you do a scatter plot and the data looks like this. Like, you know, you spend on advertising, nothing happened, but then at some point in time, if you spend a lot, then actually this is where you start seeing revenue growth. I would say this is not linear. It's more exponential. Linear would be this, right? So you got to make sure that your data, your relationship between the predictor and the outcome variable seems linear. If it's not, this can actually be corrected, and we'll talk about this with a log or other kinds of transformation. But you want that linear relationship. And then another big issue is the multicollinearity. So that's the correlation among predictor variables. Complicates the estimation of association between specific predictor variable and outcome variable. So this is especially important if we want to understand the role of a specific predictor on the outcome variable. Less important if you simply want a predictive model. So you got to think about that, and a way to address this is also to do a correlation matrix to see how, for the numeric predictor variables, how they are correlated to each other. One important point here I'll add is regarding the improving model fit via variable transformation. So sometimes some of the variables are not the way we want. So for example, some variables may not be normally distributed. And it's good that if all of the variables are normally distributed, but what we can do sometimes, so for example, in this one here that's very skewed to the right, we can actually do a transformation. That is, we can just kind of apply a mathematical equation to the values that sort of stretch it out or sort of changes dynamics, and maybe looks more normal. Now, of course, we're not changing the nature of the thing itself. We're just using a mathematical trick. But the idea is that we can actually reflect and review patterns in what's going on in the real world with the model, but if we change the model characteristics. So it is possible, it does work. We're not going to get into a model transformation or variable transformation at this point, but if you're interested in it, and if you see that one of the variables are very skewed and you want to try, maybe a log transformation is very common when we have skewed data. That would be interesting. And there's a lot of resource. Actually, there's a very good response here on Stack Exchange about this, when to use log transformation in your regression model. Okay, next we're going to talk about these model conditions for logistic regression.